A few months ago, I got an email from Katie inviting me to speak at this meeting, and she told me that this BITS group is getting together, and that they really need somebody who can talk about scientific misconduct, and that I would be the perfect person. So I'm not sure whether I should be proud of my name being associated with scientific misconduct, but I'm pretty excited to talk about this topic because I think this topic is something that's very relevant to something that's near and dear to my heart, which is the question of sort of the trustworthiness of psychology and of science generally, which is something that I will get to in a minute. I have my sort of about me slide here. A couple of sort of caveats about what I'll present to you today. So I'm a psychologist, and much of what I will present about sort of like the state of the field and specific sort of questionable research practices and things like that are based on my knowledge about psychology. I'll present some information that's relevant to other fields in the social sciences, but really sort of my expertise is in psychology, and you'll see that throughout my talk. Most of my examples have to do with psychology and things like that. But I hope that the general principles are pretty generalizable, so I'm hoping that the things that I talk about are relevant to everyone or can be sort of like tweaked to be relevant to everyone. The other caveat that I should mention is that I'll basically be presenting these ideas within the sort of framework of null hypothesis significance testing, by which I mean that I'll talk about findings as if they are true or false, which is obviously not an accurate dichotomy, but I think it's a pretty useful dichotomy when we're talking about things like, you know, the state of the literature and how research practices can sort of like inflate false positives. If you want to imagine that every time I say something like a false positive or like something that is, or something that is true, you could just sort of think of it as, you can tone it down in your mind and think about like an inflated effect size or we're overconfident in an effect or something like that. But I'll just talk about things in black and white to sort of simplify the ideas that I talk about. Okay, here is the roadmap. I'm in the bad part in the center here. So I'll be talking about researcher degrees of freedom. So far during this presentation, we've heard this approximate concept referred to as like p-hacking or questionable research practices. Researcher degrees of freedom are just like the levels of flexibility we have when we conduct studies, analyze our data, report our data, that can, if taken advantage of, lead to false positive results. And then scientific misconduct. Perhaps this refers more specifically to things like fraud. I will talk a very little bit about fraud, but I don't know that much about fraud because people don't talk a lot about fraud, or at least the fraud that they're committing. I'll mention it briefly. So one of the reasons that of course, as a scientist, I'm invested in being part of a field that is producing trustworthy knowledge. And I think I've heard this sentiment recently that we should be afraid of people mistrusting science, right? So the headlines I've put up here are just sort of like a random sample of articles that address this risk of people losing faith in science. Actually, sort of as an aside, I think that the Pew Research data suggests that people have reasonably high faith in science and aren't declining in their faith in science. But there seems to be this concern that we as scientists need to worry about the public losing faith in us. And so one of my colleagues, I think, sort of expressed this concern to me. I was giving a talk a couple of years ago at sort of an unconventional meeting with a lot of people who are not scientists. So mostly the people at this meeting, if you could call it that, are people who were like poets and writers and things like that. And so he asked me what I was going to talk about, and I was like, I think I'm going to talk about questionable research practices. And he was like, don't do that, then the people who hear you talk about this will lose faith in science. So he was like cautioning me against sort of exposing the problems within my field because he was worried that if people learned about those problems, that they would lose faith in science or become less trustworthy in science. And my reaction was sort of like, well, maybe if I tell them true things about our field and they lose trust in our field, then that loss of trust might be warranted. So that sort of led me to think about what trustworthy science does look like, and what sort of characteristics our field should have if it's to be one that creates evidence that can be trusted. And one of the first things I thought of, this is what I tell my introductory psychology students, is that evidence is the thing that makes science trustworthy, right? So as scientists, we're not just like sitting in our armchairs, philosophizing about things, not to target a specific field. And we're not just like reasoning about things or considering thought experiments, right? We're not just theorizing, but we're collecting data, right? So maybe that's the thing that makes a field trustworthy, is that we are actually collecting observations about the world. So we're collecting evidence. But I think that's not enough. So I'll give you 2 examples of evidence that I don't think increase our knowledge of the world. So the first is maybe a paper that you've maybe heard of, maybe you don't know the name of it. But this paper became famous because it was a case study of 8 children. And the conclusion in this paper was that vaccines cause autism. This paper has since been retracted. But this paper, and actually maybe you can sort of nitpick about whether this paper actually provided evidence, because I think there were some questions about the veracity of what was reported in this paper. But ostensibly this paper is reporting evidence, but that evidence is being sort of blown out of proportion and perhaps misinterpreted. Here's another piece of evidence. So the Bedford Level experiment was conducted in 1838, and what the Bedford Level experiment was designed to show was that the Earth is not round as many people claim, but in fact that the Earth is flat. And so the data or the evidence from this paper was used to draw a conclusion that I think we can be fairly confident is false. So evidence on its own is not enough to make a field trustworthy. I'm taking this slide from a talk that I saw recently at a metascience conference. The talk was delivered by Stasa Milojevic. I'm hoping I pronounced that right. I looked it up beforehand. Thankfully, she is not here to hear me butcher her name, but she is an information scientist who is interested in sort of like how the growth of scientific publications that she's observed. So she noted that there has been an exponential growth of scientific publications within recent years, and she is curious about how that translates into scientific knowledge. So what she asked was, does this exponential growth of scientific publications, so in other words, this growth of evidence, this growth of data, does it translate to an exponential growth of scientific knowledge, right? That would be nice, right? Because we are producing much more evidence and much more data. And if this were increasing our knowledge at the same exponential rate, we would be in a really great position. But her conclusion was that it does not equal an exponential growth of scientific knowledge, which suggests that we are producing a lot of evidence and a lot of data, but that our knowledge isn't keeping up with that production. So some of that data is not useful or is not advancing our knowledge. So that led me to sort of revise my ideas of what makes science and psychological science trustworthy. This here is sort of, I'm going to do something similar to what Ted did at the beginning and present what I think is sort of an idealistic vision of what science could be like or what science is worth trusting, so sort of an aspirational goal. So this writer is writing for Scientific American and is talking about why science should be trustworthy. He says, while individual scientists may make mistakes, it is incredibly rare for the scientific consensus as a whole to be wrong. I would disagree, but I'll get into that. Scientists get rewarded in money and reputation for finding fault with statements about reality made by other scientists. So he's describing a system, right, that involves self-correction. Thus, for the large majority of them to agree on something, for there to be scientific consensus, is a clear indicator that whatever they agree on reflects reality accurately. So this would be a system in which scientific consensus is something that can be trusted, right? And I think a key part of this description is that we need to be able to have a literature that is self-correcting. So this is my revision, right? It's not just that we want to have evidence, but that we want a field that is self-correcting. And I actually regret this wording slightly because I really mean two things by self-correcting. So first, I mean that we would like to have ways to minimize the production of false positive findings. And then also, and I think more consistent with this wording, ways to reject those false positive findings when they occur, right? So basically, we want to be producing data that is high quality, right? Has high evidentiary value, is contributing to knowledge. And when that data doesn't contribute to knowledge, we want to be able to have ways to remove it, right? We don't want it to be like floating around in the literature, continuing to be taught to undergraduate students, continuing to be talked about in the media, continuing to influence policy, right? So we want to minimize false positives, essentially, and have ways to get rid of them when they do occur. So the trajectory of my talk will be to start on a fairly pessimistic note by showing you what I think is evidence that currently psychology, and I think this is true of many other fields as well, is not as self-correcting as we would like. So is more there are more pervasive false positive findings in the literature. We don't have good ways of getting rid of them, and that has a sort of serious impact on the trustworthiness of the field. I'll give you a few different kinds of evidence for why I don't think psychological science is as self-correcting as it could be. The first type of evidence I'll talk about is evidence from simulations. I'll also talk about evidence from replications. So these are studies designed to test existing findings and see whether we can replicate them or find the same thing again if we repeat what the original researcher did. And then the third is just evidence from researchers, so asking researchers what they think about the state of the field. Then should be most of my focus are obstacles to self-correction, things that make it more likely for there to be false positive findings in the literature and that prevent their removal. And this is where I'll talk about briefly publication bias. The QRPs that I'll talk about, questionable research practices and p-hacking, are all very much exacerbated by publication bias and often fueled by them. And by publication bias, I mean that statistically significant findings are more likely to be published. So then I'll talk about researcher degrees of freedom, the different ways we can sort of flexibly analyze our data that can give rise to false positive findings. Briefly, I will talk about fraud as well. And then at the end, and I won't spend too much time on this because I think other people will cover this in much more detail, but I'll try to make connections between the kinds of researcher degrees of freedom that I talk about and the different strategies for improving self-correction that might sort of address those areas of flexibility. So I'll mention pre-registration and registered reports, which you've already heard a little bit about. I'll mention replication, and then open materials and data. So again, not talking too much about the details of these things, but talking about what they can do in terms of addressing the negative effects of questionable research practices. Okay, so when it comes to sort of evidence that there are more false positive findings in the field than I would like, first, evidence from simulations. So these first points are taken from an Ioannidis article where he basically did a simulation trying to examine if we make some assumptions about the field, what rates of false positive findings would we expect? And he talks about different factors that might increase those rates versus decrease those rates. So I think these points are sort of generally true across fields. First, when studies have low power, so low statistical power, this increases the risk that we'll have false positive findings, especially in combination with publication bias, right? So when the studies that are finding null effects are not being published, and we're doing low-powered studies, right, that provide less reliable estimates of effects, then overall in the field, the rates of false positive findings will increase. This is also the case when we're in fields where effect sizes are smaller. This is particularly problematic often in psychology, where we're often looking for small effects. When more analyses are done with less pre-registration, What this basically does is it increases flexibility, right? So if you have 10 different ways that you could sensibly analyze your data, this is going to increase the risk of false positive findings, especially if there's been no pre-registration in advance, right? Pre-registration addresses this, this problem by limiting the amount of analyses that you can do, or limiting the analyses that you can say were pre-registered, right? Again, for greater flexibility in analyses, right? So if you could run an individual analysis in multiple ways, that can increase false positives. These last two have to do more with incentives. So when a field has greater investment in a particular finding, right? So if you are answering to a granting agency that wants to see particular results, or you're particularly motivated by some financial interest to find one thing over another, this is going to increase false positives. And if you're in a field that heavily prioritizes statistical significance, so in other words, it's very difficult to get your findings published if you have a null finding. So these first four are increasing the production of false positive results, and these last two are increasing the reporting of false positives. And when taken together, when all of these sort of factors are working against a field, it can, according to Ioannidis' estimates, become extremely problematic. So he says, for most study designs and settings, it is more likely for a research claim to be false than true when all of these things are working against us, which he suggests is true for many fields. Moving on to evidence from replications. So the first piece of evidence here I'll talk about is from the reproducibility project in psychology. This project aims to run replications of 100 different studies and see basically what proportion of those studies in the replications did they find similar results to the original study. So it gives us a sense of the replicability of the psychology literature, or at least a subset of that literature. In the original studies, here you can see the mean effect size, 0.40. It doesn't matter if that metric isn't meaningful to you. You can see what the comparison metric looks like. And then the proportion of significant results in that set of 100 original studies was 97%, which is already evidence of publication bias, right? Obviously, if 97% of the studies in journals are significant, journals are favoring significant results. In the replications, the mean effect size was just under 0.2, so we've seen the effect size cut in half, right? And the proportion of significant results was 36%. So what this is showing us is, I think by most people's standards, perhaps some people weren't surprised by a number like 36, but I think for most of us, that's falling below what we would want for the replicability rate of a literature. This is sort of a visualization of the same project. And I like this because if you look at this sort of mound up at the top here, what you see is this nice distribution of effects that are sort of like clustering around maybe a mean of like I guess we decided the mean was 0.4, right? So these were the original studies. This is what our literature looks like. But then when we try to reproduce that or replicate that, this is what the literature looks like. So we have some significant findings that are very spread out, and then we have this huge mound of non-significant findings here. So our literature might be exaggerating the truth or the size of effects. Here's another example. This is another large-scale replication project called Many-Labs 3. This sort of repeats the same point, but if you look at the green triangles, those are the original effect sizes. They're all significant. And then if you look at the blue dots, those are the effect sizes from the replications. So as you can see, everything gets much smaller. But replications can succeed. So here at the top, we have the Stroop effect, which is an extremely reliable effect in psychological science, and it's been replicated many times. So again, things get smaller, things become non-significant. If we're using my dichotomous thinking, things go from seeming true to seeming false. And this is a summary across a number of different replication studies. So here we have the first project I showed you, reproducibility project in psychology. The gray are the results that were statistically significant in a high-powered replication study, and the yellow are those results that were not statistically significant. And then you see that across different replication projects in different fields. So we have one replication project in economics, which may look slightly better. Many labs 2 and 3. Basically, consistently, we see a really high rate of what may be false positive findings. For psychology, this isn't, so maybe you might think that it's inconsequential findings or findings that are not the ones that are influencing policy or being taught in schools or things like that. But some of the biggest findings that have sort of come under scrutiny in social psychology are findings that have become very ubiquitous within the public knowledge, right? So things like ego depletion, this idea that when we exert self-control, we sort of drain this resource. This is something that's taught in many, many intro psych classes and has influenced, I would say, over 1,000 social psychology studies. So very influential findings. The idea of power posing, which the last time I checked was the second most watched TED Talk of all time. The idea that the muscles that we move in our face influence the emotional experience that we have. Again, something that we often teach in intro psych. Something that actually one of the poets who went to this talk that I gave used in his poetry because it was like such a famous finding, and I guess he liked the sort of metaphor, right? We can also ask researchers what they think. And if we do that, so this was a survey done by Manya Baker. And according to this survey, which is across the social sciences, 38% of researchers think that there is a slight reproducibility crisis. In her data, 52% said that there was a significant crisis. I have some similar data that we collected within our own lab, this time just from psychologists. And so we asked approximately 1,000 psychologists about their perceptions of the psychology literature. Sorry that I don't have numbers on here, but this part of the pie is approximately 5%. And this proportion of psychologists said that the rate of false positives in the published psychology literature is acceptably low. Then we have the majority of people, so 60% of psychologists, saying that the rate of false positives in the published literature is somewhat higher than it should be, and we should try to lower it. And then the most pessimistic group, so 35% of our respondents said, and these are people who are graduate students and up in psychology, so who have a fair amount of expertise, say the rate of false positives in the published psychology literature is much higher than it should be, and we should take major steps to lower it. Okay, so evidence from simulations and from replication studies and from polling researchers suggests that there are more false positives in the literature than we would like, that our literature is not as self-correcting as we would like, and thus not as trustworthy as we would like. And so this next section of the talk will be reasons why that might be the case. Okay, so obstacles to self-correction. Let me start with publication bias. We've touched on this a little bit already, but this is sort of to reiterate something that I think both Sean and Ted have mentioned, which is that significant results are more likely to be published than non-significant results, right? So the Journal of Sexy Stories does not want your non-significant results, basically. And if that's the case, then this creates a bias in the literature. Some estimates within psychology suggest that approximately 5% of published studies have null results. That's sort of consistent with what I talked about from the reproducibility project, right? So it's uncommon for journals to publish null results. And this creates two problems. So one problem is that there is evidence that doesn't get included in the journals, right? This null evidence. But another problem is it creates an incentive for researchers to find significant results, right? And this affects the practices that researchers engage in, and it encourages the use of questionable research practices, which is what I'll talk about. We also know that novel results are more likely to be published than replication results. So this flies directly in the face of the idea of self-correction, right? If we want a literature that is self-correcting, we need replication results to be publishable so that they can either corroborate or call into question original findings, right? If you can't publish replication results, then we can't hope to revise our belief in findings as new evidence accumulates. So approximately 4% of published studies are replications. These numbers may have slightly increased since I included them in these slides, but I would expect not too much. And again, this leads to Ioannidis' sort of pessimistic estimate that approximately 53% of published results might be unchallenged fallacies. So in other words, they're findings that are in the literature that are being consumed by people who are reading the literature, that are being taught. They're influencing the research that new researchers are conducting, but that they might be false positives that no one has challenged because it's very difficult to publish null findings and it's very difficult to publish replications. So you can see how these features of the system that we're working in sort of snowball to create a literature that is not self-correcting and also is sort of riddled with false positive findings. This is a repetition of something that Ted talked about earlier. So he talked about looking at what happens to pre-registered studies, whether they get published or not, depending on the results of those studies. So I'm just going to repeat what he said earlier, which is essentially that when we have null results, right, the vast majority of them are not written up. Some of them are written up, and in this sample, approximately 20% of them end up being published. If we look at strong results, on the other hand, first of all, 95% of people are writing these up. And in this case, we have over 60% of them getting published, right? So obviously, there's an asymmetry here in the results that get published versus the results that don't, and also the results that don't get written up. One possible takeaway from this is that the problem with the system is that researchers aren't writing up their null results, but researchers might be not writing up their null results because they know that they won't get published, right? So it's not clear that the problem is with the researchers' decisions. Okay, so here, the publication bias creates these incentives to find p-values that are less than 0.05, at least in psychology. That's sort of our threshold for determining statistical significance. And so what that does is it encourages researchers to engage in practices that decrease p-values below 0.05. I think I do want to spend a little bit of time, actually, I know this is supposed to be sort of like a workshop-y environment, so maybe you guys will p-hack some results with me. This is a demonstration that you can find on 538's website, and it's basically a demonstration of how p-hacking can change your results to be whatever you want them to be, essentially, or how you can use p-hacking to do that. So let's see if I can. Yeah, is that okay? Okay, I think that works, right? Oh no, but that's not that.
It's not projecting.
I should have asked you about this.
No worries.
I'm going to need to get you back up here again.
Or did you?
Is it okay if we do?
Okay.
Like that? Okay. Okay, so this is the task that you're given. You are interested in whether the US economy, or if the US economy is affected by whether Republicans or Democrats are in office. Okay, so the first question I have for you is, would you rather focus on Republicans or would you rather focus on Democrats? Right, and I really do want you to answer. It's not rhetorical. Okay, Republicans, thank you. Okay, so I think that's what we're doing right now. And then we need to define our terms. Okay, so which politicians do you want to include? Do you want to include presidents, yes or no?
Yes.
Thank you. Governors?
No.
Okay. Senators?
Yes.
Okay. Representatives?
Yeah. Yes.
Okay. And then how do you want to measure economic performance? Would you like to include employment?
Yes.
Inflation? Okay. GDP?
Yes.
Stock prices? I mean, we could stop right here.
Yeah.
So you generally get the idea, right? You can see the graph moving around as I make these different decisions. I think this demonstration makes really clear this idea of researcher degrees of freedom, right? So if I haven't said in advance that I'm going to focus on Republicans and that I am going to include presidents but exclude governors, I'm going to include senators and representatives, et cetera, right? Then there are quite a few different ways that I can run these analyses. And also something that's important, I think, to note about this demonstration is that maybe you could argue that some decisions are more justifiable than others a priori, but all of them are relatively sensible, right? Like, it's sensible to include employment and economic performance, but perhaps you could imagine excluding it as well. You could imagine, if we go down a little bit to the other options below, right? You could imagine that you might want to factor in power, for instance, right? So you might want to consider how influential a politician is when you include them in your model, right? So the number of possible models that you can run increases exponentially, and you can see how dramatically the data change as you change those parameters, right? So if what we're doing is looking at the p-values of our results in order to determine how we're analyzing our data, then we can often find something that supports our conclusions when, in fact, that result might be a consequence of simply capitalizing on chance, right? And this is how we see false positive findings generated in the literature. The more flexibility, the worse this problem becomes. Okay, now I need to go back to my slides, which maybe is straightforward. Okay, so to give you another example of this, this is something that Joe Simmons came up with, and I'm stealing it before he has a chance to give his presentation. So what's reported here are the results of the study that we actually conducted on musical contrast and chronological rejuvenation. I'm going to read you the results of this study. So we asked 20 University of Pennsylvania undergraduates to listen only to either When I'm 64 by the Beatles or Kalimba. Then in an ostensibly unrelated task, they indicated only their birth date and their father's age. We used father's age to control for variation in baseline age across participants. So these are the real results of this study that was done, right? And ANCOVA revealed the predicted effect. According to their birth dates, people were nearly a year and a half younger after listening to When I'm 64, adjusted mean 20.1 years, rather than to Kalimba, adjusted mean 21.5 years. And here is the magical p-value of 0.04, which reaches a level of statistical significance. So what you see here is a real experiment that demonstrates in a statistically significant fashion that listening to one song versus another can make you younger. Obviously, again, this isn't possible, but the striking thing about this is that the way that these data are reported was pretty much the norm in social psychology before this paper was published. What you don't know is all of the other stuff that was done in order to get this ultimate result, right? So actually 34 students were run. There were conditions that weren't reported in the paper. There were a lot of other potential covariates that were included, but that didn't get analyzed, right? And so this is, again, it's just the same idea that we saw when we were looking at the political data set, right? If you have a lot of flexibility in how you can analyze your data, then if all you're looking for is a significant result, ultimately you are going to be able to find one, right? And then you can come up with a story for that significant result after you have it. All right, so I'm going to go through a few different examples of researcher degrees of freedom and talk a little bit about how they impact the interpretability of our results. The first is sometimes called Harking, which stands for hypothesizing after the results are known. This is the idea that you sort of find a result, you're looking for the stars in your data set or the p's less than 0.05, and then you're coming up with an explanation. What I just described is a very intentional process, but this process doesn't have to be intentional, right? So this process can happen sort of very unintentionally. We can see that a particular association happens to be significant, and then it can seem that we should have predicted that from the start, right? It can seem like, oh yeah, that was really sensible. We should have known that from the beginning. The percentages I'll give here are the percentages of psychologists that have reported doing this in their own papers. And actually, this used to be a way that psychologists were encouraged to write their papers, to make them like seem more interesting and to flow better and things like that. Daryl Bem wrote this down, that this was how psychologists, he recommended that this is how psychologists should write papers. And it sort of ends up looking like, you know, you're drawing the targets on after you've shot the arrows. Another type of degree of freedom is failing to report all of a study's dependent measures, okay? This is, again, relatively common. 63% of psychologists say they've done this at some point. So you include a bunch of dependent variables in your study, but it used to be the norm that, or relatively common, that they weren't all reported. And then a sort of similar, but perhaps a bit less common problem is failing to report all of the study's conditions. So in the example that I showed you, there was a song that was included in the study that was excluded from the final report. So if a condition were included when the data were run, but wasn't included in the final report. So approximately 30% of psychologists say they've done this at some point. This is problematic. Again, this is sort of an illustration of the same idea. If you imagine, let's say, a study looking at how a manipulation of power influences people's empathy, right? So you could imagine having conditions where you have a high power condition and a control condition, and you can imagine that you have, as your dependent variable, self-reported empathy, right? And so let's say you find that people who are put in the high power position report less self-reported empathy than those in the control condition, and you have a p less than 0.05. That's great. But if you also had other DVs, right? So if you also had observer-coded empathy, for instance, then that decreases the interpretability of your p-value because you could have looked at observer-coded empathy instead, or perhaps you could have combined self-reported empathy and observer-coded empathy into one sort of like aggregate measure of empathy, right? So again, increasing your researcher degrees of freedom. And then maybe you had another condition that you didn't report, right? So maybe there was a low power condition, and then you can see how this sort of like expands the level of flexibility and increases the risk of false positives. And at this point, if you're only reporting the conditions and the dependent variables that give you your significant result, but they weren't pre-registered in advance, then your p-value becomes basically meaningless. The fourth, deciding whether to collect more data after looking to see whether the results were significant. Okay, this is very related to the fifth. So stopping data collection earlier than planned because one found the result that one had been looking for. Okay, essentially both of these are deciding how much data to collect based on looking at the results. And basically, the problem with doing this is that p-values fluctuate quite heavily, especially when samples are small. And so if you are peeking at the data, you can sort of capitalize and grab the results when the p-value dips below your level of significance, and capitalize on the fact that sometimes that will happen just by chance. Sixth, deciding whether to exclude data after looking at the impact of doing so on the results. So let's say you're interested in examining a correlation between two different variables, and you predict a positive correlation. If you do this kind of thing, then you might look at your scatter plot, and you might look at these 3 data points and see if there's anything about them that might justify excluding them. Again, I'm presenting this in a very sort of like intentional, this is obviously wrong kind of way. But sometimes this is a little bit more ambiguous, right? So maybe you'll have like one really strong outlier that seems to be pulling your data away from your predicted trend. And then you notice that that participant was like, there's a note next to their name that said they were like vaping during your experiment or something like that. And then you decide like, well, could they really have been like paying attention if they were vaping? And you didn't pre-register that like vaping was a reason to exclude someone. So you can like imagine how you might end up making decisions like this, and they sort of seem justified after the fact. And sort of the same idea, if you're looking for a negative correlation, maybe you put a little bit of extra scrutiny into these 2 participants, but you don't apply that to everyone else in the study. All right. And then finally, selectively reporting studies that worked, right? So let's say you did 7 studies looking at a particular phenomenon, and you found the result that you predicted in 5 of them, but not in the other 2. Again, this is just another version of publication bias, and contributes to the file drawer problem, where null results end up in a file drawer and they can't be examined by the people who are reading the literature. So again, we have only a slice of the actual evidence that is collected. Okay, selectivity in reporting results. You might think that these kinds of questionable research practices might increase your chance of false positive findings slightly, but you might have the sort of hunch that you're probably not going to go from a p-value of like 0.2 to a p-value that's under 0.05, right? So you might feel like this isn't going to change your interpretations or your conclusions that dramatically, but actually it does change your conclusions quite dramatically. So if we focus on the p less than 0.05 column, which is this, again, the sort of cutoff in psychology, if you consider a situation like the one I described with empathy and power, where you have 2 dependent variables, in this case, assuming they're correlated at 0.5, and you're in a situation where you could report one, report the other, or report the combination of the 2, that false positive rate changes from 5% to 9.5%. And then as you start combining and adding these questionable research practices or researcher degrees of freedom together, we get up to really unacceptably high rates, like the false positive chance of finding a false positive going up to like 60%, right? So these things really add up in ways that has happened in the social psychology literature. So to sort of sum up, this is a diagram from Chris Chambers, and he sort of documents the research cycle and demonstrates how these kinds of researcher degrees of freedom, or QRPs, can sort of intervene at various stages, right? So at the stage where we're top right there, where we're generating and specifying hypotheses, that's going to influence how we design our study. But the things in red are sort of the things that get in the way, that contribute to false positives, that contribute to a less trustworthy literature, right? So having low statistical power at this point, it increases that problem. As we're collecting data and analyzing the data and interpreting it, p-hacking, right, or questionable research practices is going to increase the problem of false positives. Then publication bias up at the publishing stage, and harking when we're interpreting our data and generating new predictions, right? So if we're generating our predictions after we've collected the data, then that's also, so all of these things in red here are contributing to the false positives in the literature and to having a non-self-correcting and sort of untrustworthy literature. I said I'd briefly talk about fraud. There's just a couple of things I want to say about fraud, which are fraud has been defined as sort of fabricating, falsifying, or modifying data. So these, in a survey that was done in 2009, approximately 2% of scientists admitted to doing one of these things. I actually find that surprisingly high. So presumably this is the lower end of the reality, right? Because presumably there are some people who are not reporting that they're committing fraud. But already 2% is like, if 1 in every 50 papers that you read has a completely made up result, that's pretty problematic, right? So if you consider that that's the low end of the estimate, that becomes more worrisome. Some people speculate that these rates could be much higher than that. And also a point I wanted to make is simply that I think our definition of what counts as fraud changes over time. So in psychology now, it's been so well documented for so many years at this point that it's problematic to, for instance, hide a condition that you ran, that I would argue that it's starting to sort of get into the territory of fraud. So we all know that this is problematic, we know it's misleading, and so to knowingly do that, to knowingly withhold that information, starts to become less of an innocent, oh, I didn't know that I wasn't allowed to do that, and more problematic. So as our awareness of the problematic nature of questionable research practice changes, I think our definitions of fraud will change as well. The next section of my, I won't read that. I'm going to end there because most of the rest of my talk has to do with things like pre-registration and registered reports, and I think other people are going to cover that as well. So I'd rather take questions if you have them. Yeah.
I guess one of the things that strikes me and is how many of the problems that you're illustrating, at least in my mind, actually almost all of them, stem from the null hypothesis significance testing model and from this arbitrary division of results into significant and non-significant. It's something that we just have to abandon. It just makes no sense. It doesn't mean that p-value, we can still have p-values and all that sort of stuff, but the idea that evidence is dichotomous is really problematic. And I guess part of me feels like, I don't know, there should be a bigger push maybe for us. I agree. Correcting all the questionable research practices is important and we should be doing that, but focusing centrally on what a problem this arbitrary division into significant and non-significant statistically has created. All these problems, right? Everything you're explaining really comes from this dichotomy. And so what are we doing about this?
I guess I'll agree with part of the sentiment of your statement, but also maybe play devil's advocate a little bit. So the sentiment that we can't categorize our knowledge into yes or no, I agree with that. It's sort of consistent with the caveat that I gave at the beginning. I'm also really interested in the idea of thinking about things at least in a more meta-analytic way. So as you collect more evidence, combining that with the evidence that already exists and refining our confidence in results. But okay, so I guess one problem is that there are many times that we have to make decisions that are yes/no decisions, and so to do so, we have to decide on some kind of threshold. So we have to decide whether or not to, run a huge, expensive study on a finding. We have to decide whether or not we're going to teach findings. We have to decide whether findings are going to influence policy. So there are times when decisions that we make are yes/no decisions, and so we sometimes need those thresholds. Sure.
I think that's a really good point, and I think it is definitely true that we have to make decisions. We're making decisions all the time and setting policies and making those decisions, and I agree that has to happen. It seems extraordinarily rare and petrifying to me if those are being made on the basis of whether or not a single p-value is below or above a threshold of 0.05.
Well,
I feel like Anyway.
You could talk about it at the level of a body of evidence rather than at an individual study, which I completely agree with.
Which
that we
I
don't want
hope
to be
is the way
making.
we're making most decisions. I mean, I'm using that in a,
Right.
you know.
The one other thing I will say about the sort of like idea that categorical thinking is the source of these problems is that I don't like the idea of being in a system where we can never discard findings. And I think that's sort of the situation that social psychology has been in, where if you start saying like that we shouldn't think of things as these like yes, no, we should just think of degrees of evidence. There are some things that are so close to non-existent or so trivial that we should treat them as if they don't exist. And so sometimes I do want to say like black and white, let's stop doing research on X topic.
I think that's a really important point. I agree with you in the sense that it's important to say, look, at least for a certain kind of phenomenon that we've been investigating, there's been a lot of efforts. We have studies that were well powered to find something if they were going to find it, and we now have very precise nulls about these things.
Mm-hmm.
I think that's great. I still don't think we need to think about within individual studies of the utility of having arbitrary thresholds. I don't think that's going to help solve that problem. But I agree with you that it's important for us to say, maybe this phenomenon, we should move on and think about something.
I mean, there are
else.
certainly many people who are in favor of getting rid of NHST. You're in good company. Yeah.
I was just wondering. Oh, thank you. Hi. I was just wondering if there's like anyone trying to address the lack of replications published, as there are like, as we're like, we were talking a lot and we're discussing a lot about how to tackle the lack of null results published. But I was wondering like, what about the lack of replications, which seems also to be a high problem?
Oh, right. So the sort of bias that journals have against publishing replications.
Exactly. Yeah, the 4% only about replications only published.
Right. I know that in psychology, so those are the kinds of things I think that basically, I think they have to change at the journal level and above, because those are the places that set the incentives to run those kinds of studies. And journals, at least in psychology, have changed to some degree because of these arguments that to not allow replications to be published is to basically accept that your literature will be not self-correcting, right? So I think in response to those pressures and the results of some of these replication projects, journals have started to change their policies. So I would say that this is a wild guess. Like half of the sort of most prestigious social psychology journals now allow or encourage to some degree replications. Registered replication reports also now exist, which is a version of a registered report. So these like sort of results blind analysis process that we were mentioned earlier, where you're specifically proposing a replication study. And then I think those things were motivated in part by the results of these replication projects, right? So people chose to do these many labs projects and the reproducibility project. Many of these are sort of organized by the Open Science Foundation in order to demonstrate that we should be worried about the replicability of the literature, and thus we need to allow more replications to be published. So I think that's my perception of what's being done, but I mean, more is better. And I don't know the state of other fields. Mm-hmm. Yeah.
Thank you. All of this makes a lot of sense to me. I'm trying to think about this in the context of disciplines and subfields that don't rely as much on experimental research.
Mm-hmm.
And so just relying on that 538 example, that's arguably you have the population there and everybody's playing with the same population of data.
Right.
And so that becomes even hard to do the diagnostics of replication because what does that even mean to have a meta-analysis of studies that are not independent from one another?
Right. Yeah.
So I was wondering if you or anybody else that works in those types of fields has thoughts.
Right. I'll give the sort of cop-out answer, which is that the same like problems with flexibility and cherry picking obviously apply to having like large pre-existing data sets. So if you have like a correlation table with 10 variables by 10 variables or even 100 variables by 100 variables, obviously capitalizing on chance is a problem in those situations, right? The solutions are less clear to me, given that I think more about experimental research. But I think Fiona is going to talk a little bit about that, and so I'm just going to pass the buck and hope that she addresses that to some degree.
I'll talk like a little bit about that. The spoiler is that it's super hard and not easily solvable for many studies, but I think
Sorry, I don't want to keep peddling my own work, but this is mostly Yuri's work, my collaborator. But just in response to that, we've been working for a couple of years on something that we now finally have an R&R on, so maybe it'll come out at some point, but it's called specification curve. And the idea is that it's supposed to deal with this very problem. So like you can't really run replications on lots of observational data. And so the alternative that we propose is to lay out a population of all reasonable specifications that you could do on your data. So you say we could count governors, we could count presidents, we could count, whatever. And so you lay out all the possible combinations, all the decisions you have to make. That creates a gigantic matrix of possible specifications you could run. It might even be millions of specifications. You then take a random sample of those specifications. You run them, like Yuri's coding this in R and Stata and stuff, so you can like do it. And then it creates a graph that basically shows you what the effect size looks like as a function of the different specifications. And the graph output allows you to see what's making the effect get bigger, like the inclusion of governors is making it look bigger and the other ones. And you can also plot that against a null distribution. So what should happen what should the specification curve look like if nothing's happening versus what does it look like now? And so that allows you to sort of get around this problem of like, well, I don't know which specification to pick and we can't run a replication. So that's what we're proposing. So it's called specification curve. I think it's on SSRN if you Google it, but we'll have a final version, before 2025 or something. So.
I think that was part of the tweetings. Oh, great. All right. If there aren't any more questions or comments, let's thank Alexa for a wonderful presentation.